moved by load divided by distance moved by effort. Distance moved by load, let it be x. Distance moved by effort, let it be y. If we try to put this one into this formula, our efficiency will now be equal to, for mechanical advantage, we have this divided by, well, let me use this. Instead of having a long line like this, I want to use this sign. Velocity ratio, which is x over y, times 100%. We are going to have L over E times y over x. So what I'm going to have is Lx, that's Ly times Ex times 100%. Let's consider the value we are having here. We are given a load of 180 Newton times y. We have to calculate the efforts. We have x times 100. Let's look at the last statement. We are told that if its effort arm, that is, the distance moved by effort, is twice that moved by load. That one is talking about the velocity ratio now. Velocity ratio. Distance moved by load divided by distance moved by effort is velocity ratio. The question mark says if its effort arm or distance moved by effort is twice that of load. That is, if our x is 1, y will be 2. Okay? That is what really means distance moved by effort over distance moved by load. Okay? So, in this case, we are taking x and y to the velocity ratio. So what we are going to have now will be equal to 180 times 1. Then we are going to have 2 times e, which is 2e. Everything will be equal to the efficiency. We have been given the efficiency. The efficiency is 90%. Just say 90. If you calculate it very well, you get the value of your what? Efforts. Let's continue. This is 180. 2e will be equal to 90. 100. From there we can quickly make, we are going to have 2e times 90 will be equal to 180 times 100. And we are going to have 2 times 9, that's 180e. 2 times 9 is 18, 180, okay? We are going to have 180 times 100, so that our effort will now be 180 times 100, all divided by 180. 180 cancel 180, our effort will be equal to 100 Newton. 100 Newton. That is a simple solution to question number 4. Question number 5. A block and a tackle is used to raise a load of 250 Newton to a vertical distance of 30 meters. What is the efficiency of the system if the work done against friction is 1,500 joules? The solution to this question goes thus. The efficiency will be equal to work output all divided by work inputs plus frictional force times 100%. That is what we are going to do. The work output, as I have told you, is the work performed by the machine itself, and which is going to be the load and the distance or the height covered. Okay? And we are given the value of the load to be 250 Newton. Put it there. 250. Then the distance in this place is 30 meters. 30 meters. divided by the work input will be the same thing for the value of work output. 250 times 30 plus frictional force. We are told that if the work done against friction is 1,500, the work done to overcome frictional force is 1,500 times 100%. Then we are going to have 250 times 30 will give us 7,500. 7,500 plus 1,500, 100%. And we are going to have 7,500 divided by, this one will give us 7,500, 1,005, that's 9,000 times 100%. And if you are trying to analyze this, let's divide 7,005 by 9,000. We are going to have 0.8333 times 100%. And if you try to multiply that by 100, we are going to have 83.33333, and that is the efficiency. In short, approximately we can just say 83.3%. 83.3%. And that is the simple solution. Question number 6. The handle of a screw jack of pitched 5 mm turns to a circle of radius 22 cm when the jack is used to raise a load. Calculate the velocity ratio. The velocity ratio of screw jack is equal to 2 pi r divided by p. The p here is the pitch. The small r on some textbooks is a big r. The r we are having here is the radius. So in this case, this is 2 pi. We are given the radius. We are told to a circle of radius 22 centimeter. 22 divided by the pitch. We are told that the screw jack is of a pitch 5 mm. I want you to get something from here. We are given the value of the radius in centimeter. We are now given the value of the pitch in millimeter. Convert that millimeter back to centimeter. And when you are converting from millimeter to centimeter, just divide by 10. Okay? So, to divide 5 by 10, we are going to have 0.5. That is 0.5. Then we are going to have, this is 44 pi, 0.5. And 0.5 is as good as half. As good as half, okay? And then what you are going to have, the half of 44 is 22 pi. And if you try to evaluate this in terms of pi, which is 3.142, you get the full, but let's leave it in terms of pi. And the answer there is 22 pi. We are moving to a new topic. The topic is about elasticity. Under this topic, candidates should be able to interpret force extension curves. At the same time, the candidate should be able to interpret Hooke's law and Young's modulus of a material. The candidate also should be able to use spring balance to measure force. and at the same time being able to determine the work done in spring and elastic strength. Under this topic, we are going to consider some questions. What should be the application of Hooke's law? Let's quickly talk about Hooke's law. This is a mathematical representation of Hooke's law. The force applied on an elastic material is proportional, directly proportional to the extension produced. That is Hooke's law. Provided the elastic material, the elastic limit of an elastic material is not exceeded. That is Hooke's law. This is the force you apply on the elastic material. This is the extension produced by the material through the application of the force, and that is Hooke's law. When you want to remove this sign of proportionality, you introduce a constant. You introduce a constant K, which we call force constant, where K is equal to force constant. This is a mathematical representation of Hooke's law. We are going to use this formula to solve some questions. F is equal to Ke, our K, F over E. What is the unit of force constant? For force is Newton. For extension is meter. When you take it together, the unit of K is Newton per meter. Newton per meter. So we are going to consider all these questions to apply this mathematical relation. Question number